How did you do getting through chapter 4? Chapter 4 was mostly open systems. And as the chapter went on, you started doing a good number of practical applications and solving some homework problems that represented real practical applications. So now let's move along to chapter 5 and see what it's going to be all about. The title of chapter 5 is The Second Law of Thermodynamics. And this is one that is going to involve the introduction of some concepts that you may not be very familiar with yet. It's my hope that you're able to grasp them. I'm going to do the best I can to try to relate a lot of these concepts to some things that perhaps you already have a feel for, and then we'll go from there. So let's look at a roadmap first. So on this module, what I want to do is give you the roadmap. And this chapter 5 is so involved. Notice here that it says page 1 of 2. So I've got a whole nother bullet item list coming up. And going to try to do some review with you so as quick as I can, but I want to hit some key points that you have already covered and try to get those into your mind as you start into chapter 5. So you can see there's a number of topics that we're going to cover, some of which may be familiar to you. What's reversible? What's irreversible? But then we've got an introduction to a property called entropy you may not be familiar with at this point. And we go through some fundamentals there, okay? And then what I try to do is work you through some key points out of the textbook, some of which aren't really hammered home in the textbook. And I've tried to sort of come up with some topics that certainly are full of textbook material, but I wanted to point out some really, really important things related to them. So let's do a little review first, just to be sure we're all on the same page. So the first question is, what is a process? So try to think about that in your mind. Have you got that in your mind before I disclose the answer to you here? A process is the act of changing the state, remember that term, state, of either a closed system or an open system from one state to another state. And so I've tried to depict two examples on the left. A closed system, the tried and true piston and cylinder. Here's my sketch. I've tried to show Q in, W out, tried to show the control surface, and try to depict that we're moving from state 1 to state 2. Does that look familiar? Closed system undergoing a process. How about on the right-hand side? An open system undergoing a process. And by and large, we're going to focus on open systems that are steady state, steady flow. Think about that back in your mind. Okay, so what is a process? I think you've got it. It can be a closed system, it can be an open system. Excuse me. Now, next question. What is a cycle? Well, you remember what a cycle is from previous textbook work. Well, a cycle starts and ends at the same state. And so I've kind of created an example problem cycle. And here's my sketch. I've got a closed system, piston and cylinder, undergoing a set of 3 processes, 1 to 2, 2 to 3, 3 to 1. And I've got to say, I've got an ideal gas in here. So remember, PV equals MRT. I'm going to say that all 3 of these processes occur in a quasi-equilibrium manner, okay? And what's our object? And so, of course, the first thing you see is, okay, my review is, I remember a PV diagram. I remember generally what a cycle is all about. We start and end at the same state, in this case, state 1, 1 to 2, 2 to 3, 3 to 1, okay? And here's our objective in our example problem review is we'd like to not necessarily go through numbers, but in our heads, could we figure out a way to determine W net? Could we get to a number? If we had some numbers to mess with, could we get to a specific number on W net in kilojoules? Could we do that? I hope so. Let's go through and sort of review. Let's look at process. We'll work through the process. We need W net. If we can get the work for each process, we'll add all 3 of them up, and that'll be W net. So let's work on process 1 to 2. Okay, let's see. And what we also want to do is use the first law for a closed system to figure out, is heat added or heat rejected? So let's do that. 1 to 2. Work out from 1 to 2. Integral PDV, area under the curve. We just write down W out as 0, right? So that one's easy. The area under the curve is 0. Let's write the first law for a closed system. Qn minus W out, that's 0, equals delta U, and that's going to be M times the integral of CV dt. Okay, and so rather than going through numbers, observe that T2 is bigger than T1. Remember that constant temperature lines are hyperbolas on the PV diagram, and so therefore by inspection T2 is a bigger number than T1. T2 is bigger than T1. So what's Qn going to be? Is it going to be a positive number or a negative number? Okay, 0, M integral CV dt with T2 be bigger than T1. This right-hand side is going to be a positive number, isn't it? With T2 being greater than T1. So we can simply write down heat is added in process 1 to 2. Qn from 1 to 2 is a positive number. Okay, 2 to 3. 2 to 3. How about the work out? The work out. Could you figure out the heat added from 2 to 3 if you had the input numbers, mass, T2, V2, things like that? I would say, of course you could, right? Because work out is the integral of PDV for 2 to 3. The temperature is constant. If you got an ideal gas, P is equal to MRT over V. So do you remember, you'd have a log term. You could get a number for that. And let's see, V3 is bigger than V2. So can you see, and with your eyes, you see that W out from 2 to 3 is a positive number. You could do the math, but it's a positive number. All right. How about Qn from 2 to 3? Let's see. Let's look at the right-hand side. M delta U, M integral CV dt. Well, T3 equals T2. So the right-hand side is 0. So is Qn going to be a positive number or a negative number? Okay. If I switch this to the right-hand side, Qn is a positive number, right? So heat is added in process 2 to 3. So it's a good thing. It's a good review thing to pick up as you get into chapter 5. Process 3 to 1. Let's see. Work out from 3 to 1. That's easy, isn't it? It's the area under a rectangle, and it's a negative number because you're integrating right to left, and you could do the math and you could get a number for that. But do you see that W out from 3 to 1 is less than 0? Area under the curve, see it with your eyes. You got the experience, you got it. So let's look at Qn. Qn from 3 to 1. All right, so let's see, Qn, what is it? Minus W out. Well, that's less than 0, equals the change in internal energy, mCV integral CV dt. Wow, okay, well, what's this right-hand side going to be? I'd suggest that it's going to be less than 0 because T3 is a bigger number than T1, okay? And so however you do this integral, you're going to get a negative number for the integral. Let's see, we're going to add a negative number to both sides. And so my claim in your review is that Qn from 3 to 1 is going to be a negative number, and we're going to write down heat is rejected in process 3 to 1. Heat is rejected. Qn is a negative number. Okay, we're getting near the end of the review here. Okay, so how would you, if you had the numbers, what would you do? Of course, you would observe that the net work for this cycle is the area contained within this. It's not a triangle, but it's a right angle shape. Okay, and so the area in there is greater than 0. You'd simply add those 3 numbers up. One of them was 0, and you get a number. Okay, so W net is going to be greater than 0. Because you're coming, remember the clockwise arrow trick? Okay, so you got a clockwise arrow inside your cycle that says W net's going to be greater than 0. Another thing you need to write down or recognize, I hope, is that where is heat added? Can you can you remember where heat was added for this example problem? Heat was added in process 1 to 2 and also in 2 to 3. And from previous work, we're going to call that Q sub H. Q sub H. So we're going to add up all the heats that are positive numbers. And then we're going to add up all of the heats that are negative numbers, and we're going to assign that to a variable called QL. And so do you notice here that I've got QL? I'm being a little tricky. I'm going to say that's equal to the absolute value of Qn from 3 to 1. So QL is just going to be some number. So I've got a QH term where heat is added, and I've got a QL term where heat is rejected in our example cycle. Okay, so now a little more review. The first law of thermodynamics for any system operating in a cycle. We have covered this already, but it's going to be so important for you to remember this. The first thing I do as a problem solver is when I've got a cycle, I draw this schematic. And our example was a heat engine, or also called a power cycle. So I've got QH, that's where all the heats are added into the closed system, the piston and cylinder. We have a number that we came up with called W net that was bigger than 0. We've got this arrow pointing out, and then QL coming out of the system, and that's going to be the heat rejected. And so for this system operating in a cycle, for any system operating in a cycle, there are basically two statements of the first law. One is for our schematic, QH minus QL equals W net. Okay, that's important. That's for, you can solve problems with that. Now, if you're graduate school bound, maybe not quite as obvious, it says the cyclic integral of heat in exactly equals the cyclic integral of work out. That's not quite as actionable, is it? But that is the correct mathematical way to state the first law for any cycle. So if you're thinking about graduate school, that's going to be your starting point for graduate level thermodynamics. Now that was a closed system, wasn't it? I want to take you through a mental exercise to prepare you for chapter 5. How would you build a cycle out of a number of open systems? How could you as an engineer build, I've got a bunch of open systems. How can I build a system operating in a cycle with those things? I think you could do that. I'm going to suggest that you could figure out how to do this. I've taken some screenshots of the 4 key components of a steam power plant, okay? You could start with a turbine. You've done some turbine problems now, okay? You start at a high pressure and end up at a lower pressure. You make power, W dot, okay? You got to condense that steam. You got steam coming out of the back end of the turbine. You got to condense it somehow. We condense that steam with a condenser. It's a heat exchanger. You had a problem like that back in chapter 4. Well, that enables you to get liquid condensate, saturated liquid condensate back, so you can send it into a pump. And you had a pump problem in chapter 4. Here's your feed water pump. And what is that pump going to do? It's going to increase the pressure of that liquid water back up to a high pressure so you can send it into a steam generator or boiler. So here's our pump. We're going to send that back to the boiler, and we've got a system operating in a cycle where we're making net power, W dot. Well, let's go through that mental exercise. So I know I'm taking some time up, but just bear with me so that you can be prepared to do well for chapter 5. Let's start with a sketch, okay? And let's start with the turbine. That should look familiar to you because you've had a turbine problem, steady state, steady flow, one inlet and one outlet, right recently in chapter 4. There's my sketch, okay? The next thing I'm going to do is at state 2, I'm going to add a condenser. That's a heat exchanger that's exchanging heat with a low temperature reservoir, okay? And we're condensing the steam, the low pressure steam at state 2 back to saturated liquid water, state 3. So I've got steady state, steady flow, one inlet, one outlet. You can do this. Next component is the pump. You've analyzed a pump out of chapter 4, okay? So I've got same thing here, steady state, steady flow, one inlet, one outlet, pump. Now, you know that it takes power to drive a pump. Of course, that's common sense. So W dot of the pump is less than zero. And so we would compute our net output power by adding these two numbers together, W dot of the turbine and W dot of the pump. That'll give us W dot net. Well, we got to complete the cycle. So we've got a system operating in a cycle. We do that by adding a steam generator. It's a heat exchanger again. And so you've got some experience with a heat exchanger. You're adding heat to compressed liquid water. You're turning it into superheated steam. And that's what enables you to complete this cycle. So getting you ready for chapter 5, notice I've drawn my block arrow going clockwise. So the sketches kind of fit together. Okay. And it should make sense to you. Okay, so I'm kind of blazing through it. You can replay if you need. Do you see that with my sketch, if I draw a control surface around all 4 of my open systems, do you see that I have created a closed system? Okay, it's operating at a steady rate. Operating at a steady rate. Let me move my picture here. Okay. And so this closed system that I've got encased in dashed red line is operating at a rate, but it is a closed system. It's going to be so important for you as you get into chapter 5 and move into chapter 6. Okay, so we've got a little repeat that I said we took 4 open systems and pieced them together to form a closed system operating at a certain rate. Here's my schematic that it should look like. I've noticed that, oh, I've missed a dot. Look at that, careless. I should have a dot over top of my WNet, W dot net. I got my dots over top of my Q's, okay? And it looks like I got it here. First statement of the first law for a system operating in a cycle at a steady rate. It looks identical to the piston and cylinder one single cycle, except it's got dots over top of everything. It's all about the dots. So we have reached the overview of chapter 5, called the second law of thermodynamics. That's what you're going to be talking about. It is possible that some of these concepts will blow your mind. I want you to hang in there, keep plugging away, because here's what you're going to be able to do as an engineer once you finish this chapter 5. You're going to be able to tell if a proposed system operating in a cycle is possible or impossible. That is a powerful engineering skill that is worth some money to you. So not everybody in the world can do this. So if a salesperson proposes a system operating in a cycle to you with certain numbers associated with them, you as an engineer will be able to evaluate, is this salesman trying to sell something to me that's impossible, or is it possible? So again, very powerful skill that you will develop for a system operating a cycle once you finish chapter 5. So that's kind of cool. And so that's going to be a saleable skill that you will have. And then moving into chapter 6, we're going to go even more in depth into the second law of thermodynamics. Chapter 5 is all about the second law, but you have to have mastered the continuity equation and the first law to be able to do well on quizzes and tests moving into chapter 5. So I hope that review helps you review and get ready as you start into chapter 5.